Hi, welcome to our last little section of chemical kinetics, and ultimately this is probably the most important section, and that is catalysis or catalysts. And catalysts are things that speed up the rate of a chemical reaction. So that's why it's so important, because reactions, if we can get them to go faster, that's economically viable, or if it's our body, right, the reactions need to take place at a certain speed to keep us alive. So catalysts are things that speed up chemical reactions. But importantly enough, they are not consumed, so they're not used up in the reaction itself. So it wouldn't be any good having a catalyst that just got used up, because we'd have to keep making it to speed up the reaction. We constantly can use it, right, and reuse it and reuse it. And how do they work? Well, we can speed up a chemical reaction by lowering the amount of energy the molecules need to collide with to undergo a reaction. And so that is the lowering of the activation energy. And this lowering of the activation energy is normally achieved by the provision of a completely different mechanism. So you provide a different mechanism. So there's another way the reaction can take place. So we'll investigate these different mechanisms here in a second. But here's an example of one. We mentioned earlier that the chlorofluorocarbons, so those propellant molecules, catalyze the decomposition of ozone. In fact, what it normally comes from is the fact that the chlorine atoms themselves can act as a catalyst. So chlorine can catalyze the decomposition of ozone, and it is not used up in the process. So a single chlorine atom can catalyze millions upon millions of these ozone molecules and break them down. And so it provides a new mechanism. So the mechanism looks something like this. So the chlorine atom by itself can react with ozone, and it can convert it into oxygen molecules plus chlorine monoxide. And that chlorine monoxide, can react with another ozone molecule and reconvert the original chlorine. So that's why it's a catalyst, because it is not used up in the reaction, and a couple of oxygens. And if this mechanism is faster than the previous one, right, if the overall activation energy is reduced, then this chemical decomposition reaction will take place many times faster than the natural process. In fact, we can draw an energy diagram for what's going on here. So if we draw energy or potential energy versus the reaction coordinate or reaction progress, then the normal uncatalyzed reaction, where we start with a couple of ozone molecules and we convert them to a trio of oxygen molecules, right? This is assuming it's exothermic, remember. The normal reaction would take place like this, right? So we'd have a two-step process. So we got kind of little two humps here. And this is the uncatalyzed reaction. And we said the first step is the rate determining step. And that is because if you look at the activation energy for the first step, it is really large. And for the second step, it's essentially going from here to here, so it's very, very small. Now, if you introduce a catalyst, if you introduce chlorine, you can get it to go along an alternate pathway. So if maybe the reaction with chlorine is much easier, then you can end up with a process that looks something like this. So this would be the catalyzed process. Okay, if I can spell catalyzed, with the chlorine, you can see the activation energy now is much, much smaller. So the catalyzed activation energy is much smaller. So the reaction takes place much more rapidly. Now, look at the energetics. It turns out it gives it exactly the same amount of heat off, going from ozone to oxygen. So it doesn't affect the heat given off by the reaction. We'll see later on it doesn't affect the equilibrium. It turns out the equilibrium constant is going to be related to these two relative energies. All it does is it makes it easier to go over it. So imagine you're kind of like digging a tunnel through a big hillside. It's a lot easier to go through the tunnel than it is to go over the very tippy top of the hill and down the other side. So one last little thing before we finish this chapter, and that is the idea of homogeneous versus heterogeneous catalysts. And homogeneous means that the catalyst is exactly the same phase as the reactants. And in a heterogeneous catalyst, it is a different phase. So by phase, I mean solid, liquid, or gas typically. So let's look at the breakdown of peroxide. So if you buy hydrogen peroxide from the grocery store, it is typically dissolved in water, maybe a 3% solution, and it will break down and form water and oxygen gas. And it turns out that you can catalyze it using two different catalysts. So one catalyst is you can use iodide ions. And so iodide ions will catalyze the reaction. They'll speed it up. And they would be an example of a homogeneous catalyst because the aqueous phase, the liquid phase, right, is exactly the same as our reactant. However, you could also use a platinum catalyst. So you could use solid platinum as a catalyst as well. It would also speed up the reaction, and we would call it a heterogeneous catalyst because it's a different phase. Now, you might just say, well, why bother with the names? Well, one interesting thing is that if you've got a solid catalyst, we said it's not used up in the reaction, how do you separate it out when you're done with the reaction? If it's a solid, you can just filter it off, piece of cake. Whereas if you have the same phase catalyst, it costs a lot more money to separate out your catalyst. And so at least industrially, right, we prefer these heterogeneous catalysts. They're just much easier to separate from the reactants themselves. In fact, the catalyst in your car in the tailpipe is platinum, palladium, and all these expensive sort of inner transition metal elements, and it catalyzes the breakdown of the exhaust gases. And because it's a different phase, it's very easy to keep apart from the gas that's produced in your car. Awesome sauce.